so this is my first video in a while. It is for, among other things, we will be calculating the current and voltage across all of these resistors. I'm also doing it to test out this new microphone headset thing I got that kind of makes me feel like I'm a helicopter pilot. Okay, so we've got this whole circuit, all resistors, and we're going to find the current and resistance in each one. What we want to do is find the equivalent resistance first, step by step. Now, let me squeeze this guy over a little bit, something like that. Okay. So first thing we want to do is either combine these two resistors who are in series or these two resistors that are in parallel. Doesn't really matter. I'll go ahead and do the parallel one first. So it'll look like this once we combine them. This is still R4, R3, and I might call this R12. And here's my battery up here. So the only thing that changed is I combined R1 and R2 into this R12. So the equation is going to be that R12 is equal to 1 over R1 plus 1 over R2. 1 over that, or you can just raise to the power of negative 1. Which is what I usually do. So that is 1 over 6 plus 1 over 18 inverted ends up being 4.5 ohms. So R12 is 4.5 ohms. So in doing this process, we are going to end up with a lot of different numbers floating around everywhere. It's one good technique somebody mentioned to me was to make a table. So I'm going to just make a table here of the resistances, voltages, and currents in all of these things. So here we go. So if we're going to talk about resistor 1, resistor 2, resistor 3, and resistor 4, but now we also have this resistor 1, 2 that I can add to the table. Now this table is just to keep track of our answers as we go. It's not really a formal necessity. So I already know these resistors. This was 18. And R12 is 4.5 we discovered. Okay, moving on. So we've taken one step to combine to get towards our equivalent resistance. Next, we'll combine, well, all three of them. We can just combine all three of these in series now. So that's easy. And it'll just look like this in the end. And that would be, well, I could call it R1, 2, 3, 4, but that's annoying. I'll just call it R equivalent, because it's the last one. So, the equivalent one. And so because they're in series, this R equivalent is just going to be R3 plus R4 plus R12. So that's 1.5 plus 4 plus 4.5, which makes 10 ohms. Okay, so I mentioned that we were finding the voltage and current in all of our actual resistors from the original picture, so you might be wondering why I'm finding equivalent resistance. Well, the reason is, look at all these unknowns we have. There's like 8 of them or something that we want. That's way too much to solve in this big complicated picture with all these resistors. So what we've done here is simplified the circuit in a couple steps, as many steps as it takes, to get down to one battery and one resistor. Because, well, guess what? Now I know the voltage. The battery hasn't changed. This is still 10 volts. Now because the battery and this resistor are in parallel with each other, we know that the voltage in the resistor is also 10 volts. Okay, so remember, in parallel, voltages are the same. So these two are in parallel, so the voltage across R equivalent is 10 volts. So I should put my units are ohms for resistance, volts for voltage, obviously, and they're going to be amps for current. Okay, so that's the voltage. Now as for finding the current, well, we have Ohm's law, right? V equals IR. If we arrange that, we get I is equal to V over R. So the current in the equivalent resistor is equal to the voltage in the equivalent resistor divided by that equivalent resistance. The voltage is 10 volts across it, like we just discussed. The resistance is 10 ohms, so 10 divided by 10 makes 1 amp of current running through the equivalent resistor. Okay, now that's not even anything that we wanted. We're looking for these values in the original circuit. So let's work our way back. Now we're going to step back through all of our sub-circuits here. Now that we know both the voltage and the current in our equivalent, we need to figure out which piece of that information is helpful to take back to our previous picture. So note that our equivalent is a series combination of resistors. What we know about series is that the current in all components that are in series is the same. Okay, so whatever the current was going across these two dots in my final picture here is also going through these two dots. Right, that is those are the sides of my equivalent resistor. Broken back up, we still have that same current going through all of these resistors. So I now already know, well, the current in 1, 2, that is equal to the current in the equivalent resistor of 1 amp. And that's the same for R3 and for R4, because components in series all have the same current going through them. I'm going to fill that out on my chart. So I have 1 amp in the 1, 2, 1 amp in the 4, and 1 amp in the 3. Okay, now that I know both resistance and current for several more elements, I can use Ohm's law again to find the voltage. So V equals IR. That means the voltage, for example, in resistor 3 is going to be 1 amp times 1.5 ohms, which gives me 1.5 volts. Okay, these ones make it easy, right? So I'm looking at V equals IR. 1 amp times 4 ohms makes 4 volts. 1 amp times 4.5 ohms makes 4.5 volts. Alright, it's not always that easy. Okay, so now I know everything about this circuit, right? I've solved for everything there. I know the voltages. So now, working back to my final original circuit, R12 was broken up, right? We took R12, okay, that's between those X's, and it broke up to be here, right, in parallel. That breaks into parallel. So it's in parallel, like we mentioned earlier, voltage is the same. We know that the voltage in R1 has to be equal to the voltage in R2, and that's the same as the voltage in R12. So that voltage in R12, that was 4.5 if you look at our chart here. So that's also going to be the voltage in R1, or R2, and in R1. Okay, and now we can calculate the current. So again, current is equal to voltage divided by resistance. Okay, so didn't do this one yet. So current is voltage times so for resistor 1 there, we have 4.5 divided by 18, which is 0.25. And for R2, we have 4.5 divided by 6, which is 0.75 amps. Okay, and so we have answered the original questions, which were to find the voltage and current in each of our resistors. If you look at our chart here, we know the voltage in resistor 1, the current resistor 1, and so on. And we also found these guys, which aren't really part of the question, but they helped us find our answer. So to recap, to solve a problem like this, you combine your circuit down to its equivalent resistance step by step, and then you carry pieces of information back, solving for everything in the circuit each time. When you have an equivalent resistor that breaks into series, you know that each of those resistors will have the same current as their equivalent resistor. But if you have an equivalent resistor that breaks up into parallel, you know each of those resistors is going to have the same voltage as their equivalent resistor had. Alright, so it's just series versus parallel rule to remember. And there you have it. And that sounded terrible. I'll need a new microphone.